Hi, my name is Aiping Zhang, a master student of Nanjing University of Aeronautics and Astronautics. This is the presentation of our paper, Learn to Align, a code alignment network for code clone detection. In this paper, we mainly focus on the code clone detection task, including four types of clones. Formally, type 1 denotes that two code snippets are identical except for spaces, blanks, and commas. Type 2 means the same code snippets except for the variable names, type names, literal names, and function names. Type 3 means two codes are almost identical except for several additions and deletions on statements and name changes. Type 4 means two code snippets accomplish the same functionality but have different structures or syntax. From Type 1 to Type 4, accurate detection is getting more and more difficult. Many methods recently use deep learning-based algorithms to handle difficult code clone types, which includes three parts. First, transform code fragments into abstract syntax trees or program dependence graphs, and then use neural networks to extract feature representations, and finally, calculate the similarity to make decisions. However, they ignored the code misalignment problem on Type 3 and Type 4, that is, adding or removing several statements or using a flexible structure to implement the same function. This phenomenon is common and also can be found in some benchmarks, such as Big Clone Bench dataset, where such kind of clones accounts for more than 95% of the total number. Even if we have extracted the features of codes, this issue still exists. The reason is that previous methods usually calculate the ratio of feature representations of two similar codes. However, due to the code misalignment, the ratio of each statement feature always shows low similarity, and the global pooling also keeps the low similarity. This could ultimately lead to poor performance. To address this issue, we present a novel code alignment network to perform code alignment in a data-driven way. This is the overview of our method. Specifically, we follow ASTNN to pass source code fragments into abstract syntax trees, which are further divided into finer granularity statement trees that are encoded into vectors by a small statement encoder. We then design a bidirectional causal convolutional neural network to model the structural and contextual information for code fragments. Causal convolution is used for temporal data, which ensures the model cannot violate the order. Formally, the bidirectional causal convolutional layer concatenates the forward and backward directional features to obtain the output feature f, and inspired by the inception network, we designed the block, which includes a bidirectional causal convolutional layer with three different convolution kernel sizes to capture information of large receptive field. Finally, we propose two independent code alignment strategies to deal with the issue of code misalignment. As shown in the picture, we not only align code Y with code X, but also align code X with code Y in a bilateral way. The reason is that align one code to another usually destroys the structure of the first code. Therefore, in order to maintain the structural information of two code fragments, we calculate two aligned features. After that, we calculate the residuals between the aligned code representations and the extracted features. Since the residual is a two-dimensional tensor, we apply a global max pooling along the sequence dimension to obtain two vectors V subscript xy and V subscript yx. Then we fusion the two vectors and use a fully connected layer to map dimensionality from D to 1, followed by a sigmoid operation. Finally, we use a binary cross-entropy loss to guide the training process. Our method obtains state-of-the-art performance onto popular datasets. bclone bench for Java language and OGclone for C language. The two code alignment strategies can constantly improve the performance compared with the baseline models, and sparse reconstruction-based code alignment has no extra parameter and performs a little bit better than attention-based code alignment. And this is the illustration of the statistical distribution of similarity differences before and after the alignment operation. The horizontal axis represents the similarity after alignment minus the similarity before alignment. The vertical axis represents the numbers of code pairs. And we can see that after applying the code alignment operation, the similarities of positive code pairs are increased. Meanwhile, the similarities of negative code pairs are decreased, demonstrating the effectiveness of code alignment. This picture is an example of the alignment results. We show three statement pairs that have alignment scores greater than 0.5. We can find that our proposed strategy obtains astonishing code alignment performance. Therefore, it is unsurprising that the code alignment would promote code clone detection since it eliminates interferences such as locations, and allows the model to intently focus on detecting similar codes. That's all for my sharing. Thank you for listening.